Hello, my name is Santiago Mol Lopez, and we're going to see derivatives of elementary functions. We will also learn properties of derivatives. The requirements are to know how to operate with exponents, to know how to work with rational numbers, and to be familiar with elementary functions. Let's start with a review of the most important derivatives. For example, if we consider the constant function, you must know that its derivative is 0. Also, if we consider the identity function f of x equals x, its derivative will be 1. Then, the derivative of x raised to the power of n, attention, because this is one of the most important, its derivative is, look at the scheme, n by x raised to the power of n minus 1. You have to observe that the exponent comes down in front, and we subtract 1 from the one that was there. This is very important because most of the derivatives are going to be based on this property. Let's continue with the properties. We have that if a function is sum of two functions, the derivative of f of x in this case would be the derivative of g of x plus the derivative of h of x, as you can see in the formula. And what happens when a function is multiplied by a constant? Imagine that f of x is a function that consists of a number by the function g of x. In that case, what you do is to differentiate the function g of x and don't touch the constant. The constant remains when you differentiate. The constants that multiply, of course, because any constant that you add, like the ones of the first kind, would become 0. Very important. The constants that multiply remain when you differentiate. Let's see some examples. The simplest function I can think of, for example, is x squared as polynomial of second grade. What is the derivative of x squared? Well, if we follow the rule that we have seen previously, that would be 2 times x raised to the power of 2 minus 1. We subtract 1 from the exponent and bring down the original exponent in front. Then if you want, of course, you can simplify. You would have 2 times x raised to the power of 1. I still keep the 1, so you know it comes from subtracting 2 minus 1, but you do not have to write it there. Let's look at example 2. Another polynomial, x to the 5th. In this case, it is a power x raised to the 5th. It is very easy to differentiate it. Can you guess what the derivative will be? The 5 will come down, we subtract 1 from the exponent. It would be 5 times x raised to the power of 5 minus 1, which would be 5x to the 4th. The mechanism is not complicated. I insist, lower the exponent and subtract 1 to the 1 that there was. For example, if we have x raised to the power of 10, then what we would have would be 10 times x raised to the power of 10 minus 1. The same technique as you can observe, the 10 goes down, and we subtract 1 to the exponent above. I would be left with 10x raised to the power of 9. Note that this property is useful for much more than just these functions. Look at this property. If we have 1 over x raised to the power of n, that can be written as x raised to the power of minus n. These are exponents. I assume you know how to work with powers. It was mentioned in the prerequisites. If not, this property can sum up a little what we are going to see now. The thing is that, look at the property that we had seen before. I have to go back a little. In this property, here for now, I have not put any requirement to the n. Then we will see if there is any or not. But in principle, this n could be positive or negative. We are going to try to apply this property to the new case that we have here. And now allow me to go a little more forward. Here, we are going to try to apply that previous property, and this one, to some new examples. Look, we imagine that we have the function 1 over x squared. This, in principle, with the initial formula, we wouldn't have any idea how to differentiate it. But if we apply the note that we have seen a little while ago, we can rewrite it as x raised to the power of minus 2. Now I can apply the formula that appeared at the beginning. I can bring down the minus 2 in front and subtract 1 from the existing exponent. Observe, the minus 2 goes forward, and in the exponent I would have minus 2 minus 1. Now minus 2 minus 1 is minus 3, and it simplifies a bit. Here, I have rewritten it at the end as minus 2 over x raised to the power of 3 using the same note that I saw at the beginning. Let's see another example. 1 over x. Here, the exponent would be 1 over x raised to the power of 1. With the same note as before, that could be rewritten as x raised to the power of minus 1. Let's differentiate this function, which fits the formula we saw on the first slide. As you can see, the minus 1 comes down in front and we subtract 1 from the exponent. How would it look now? Minus 1 is minus 2. Minus x raised to the power of minus 2. And then, of course, if you want to rewrite it in fractional form, then you put the minus 1 that comes from this negative sign, and x raised to the power of minus 2 can be written as x squared in the denominator. Another example. Now the only thing that I have included is a constant in the numerator. Remember that any constant that multiplies is not touched when differentiating. Let's see how this would look like. This, rewritten with the previous note, would be 3 times x raised to the power of minus 5. Let's differentiate this. The 3 remains, the minus 5 of the exponent goes down, and x will be raised to the power of minus 5 minus 1. We subtract 1 from the exponent. We simplify this a little, and I would have minus 15x raised to power of minus 6. Obviously, minus 15, because 3 times minus 5 is minus 15, and minus 5 minus 1 is minus 6. Let's expand our range a bit, with the formula I have mentioned is important a while ago. Look at the following expression. It's the m-th root of x raised to the power of n. Something quite complicated that at the beginning we wouldn't have the key to know how to differentiate it. If we apply this note, this can be written as x raised to the power of n over m. That is, x raised to a number. And this does fit the derivative formula we had at the beginning. Let's see an example. Imagine that someone asks us to calculate the square root of x, an unthinkable thing with just the initial formulas. The square root of x, according to this formula, could be written as follows. Notice that x is raised to the power of 1, and the square root would be 2. This could be written as x raised to the power of 1/2. This I know how to differentiate. Of course, it's x raised to a number. That number would come down in front, and we would subtract 1 to the exponent. Observe. Here you have it. 1/2 that came down in front multiplied by x raised to 1/2 minus 1. Of course, 1/2 minus 1, you should know what it's worth. It would simply be minus 0.5 or 1/2 in the form of a fraction, as you can see. Is it necessary to adjust this? Yes, we always like that. In the end, you simplify, and you write it in a more simplified way. Notice that here x raised to the power of minus 1/2 after applying the initial note. Not this note that you have up here, but the previous one. This would be 1 divided by x raised to the power of 1/2 with the positive exponent. And now I'm going to redo the square root of x raised to 1/2. It would be 1 divided by 2 times the square root of x. This is how this derivative looks simplified. My advice is that you learn by heart this derivative. The derivative of the square root of x is always 1 divided by 2 times the square root of x. It appears so many times and in so many problems that it is much easier to apply it directly than to apply all the steps. But it's always good to have at least the necessary tools to deduce it at any time in case you forget. Let's see another example. In this case, we have already put a cubic root of x squared. We have changed the m and the n to larger numbers. As you can see, applying this note, the cubic root of x squared can be written as x raised to the power of 2/3. We differentiate x raised to a number applying the same rule. 2/3 comes down and multiplies x raised to 2/3 minus 1. Clarification. 2/3 minus 1 is minus 1/3. As it has the negative exponent, we put it down positive, and we reconstruct the square root here. In this case, the 3 is the m in the formula, and the 1 is the n. Therefore, we would have 2 over 3 times the cubic root of x. Here I put 2 formulas in general. If m is greater than n, then the derivative of the mth root of x raised to the power of n has this form. I think it is not necessary to learn this formula. It is better to deduce it every time except the most used, as for example, the root of x. And if n is bigger than 1, then the derivative of 1 over x raised to the power of minus n is, in general, minus n over x raised to the power of n plus 1. What have we seen today? We have reviewed the derivative of a constant, the derivative of x, which is 1, and the derivative of x raised to the power of n, one of the most important derivatives and the ones you will apply the most. I hope that all this helps you. Thank you very much for your attention.